Welcome to the Deep Dive. Today, we're doing something a little different and I think really crucial. We were taking an incredibly dense industrial safety program.
The kind of thing nobody reads for fun?
Exactly. It's written in pure compliance speak for a very specific worksite. We're going to crack it open and pull out the absolute core life-saving knowledge.
And our source today is the safety manual for industrial gas cylinders, developed for a site known as the Rhino Project.
Right.
We're pulling from some heavy-hitting standards here, things like the Indian gas cylinder rules from 2016, and even international benchmarks like OSHA.
So this is serious validated stuff.
Absolutely. It's aimed at field operators, maintenance crews, anyone who gets near these things. The goal is simple: a zero-incident workplace.
And for you listening, this is your shortcut. We're going to get past the generic warning, flammable stickers, and into the real chemistry.
I mean, what is the actual non-obvious difference between oxygen and acetylene?
And why does one wrong move with either of them turn a simple metal tank into, well, a potential catastrophe?
What's really fascinating and maybe a little scary is that this isn't just a theoretical risk. It's a real statistical problem.
Oh.
Yeah, if you look at reports from PISO, that's the Petroleum and Explosive Safety Organization in India, they estimate that something like 20% of all industrial accidents involve gas cylinders.
20%.
20%.
That is a massive number. That means these things we see sitting quietly in a corner are one of the biggest physical risks on any given site.
It immediately changes how you look at them, doesn't it?
It really does. Okay, let's unpack this. And I think we have to start with the gas that fools everyone. Oxygen.
The silent accelerator.
Right. We need it for welding, for cutting, even for medical support on site. But it's tricky.
It is, because it's a powerful oxidizer, and people forget that oxygen itself isn't flammable. You can't just light it on fire.
You can't.
But if you already have a fire or any heat source and you introduce pure oxygen, it's like pouring gasoline on it, but on a chemical level.
It just accelerates everything.
Geometrically. Fires burn hotter, way faster, and much more violently than they ever would in just normal air.
So the danger isn't the cylinder exploding on its own. It's that the cylinder turns a small fire into a massive, uncontrollable inferno.
That's a huge part of it. But the number one danger, the one the training manual just hammers home again and again, is contamination.
Okay.
This is where a small human error meets some very volatile chemistry. If you get highly pressurized oxygen in contact with oil or grease,
Even a
tiny smear on a valve thread or a fitting, it can cause an immediate, spontaneous, and very severe reaction.
So that little bit of lubricant you thought was helping just became an ignition point.
The second you open that valve, it can cause a flash fire or an explosion. It's that serious.
Wow. That just reframes the simple act of connecting a regulator, doesn't it? Cleanliness is everything.
It's paramount.
Okay, so that's the silent threat. Let's talk about its enemy in the storage rack. Dissolved acetylene, DA.
Right. If oxygen is the accelerator, acetylene is just pure inherent instability.
This is the fuel.
This is the highly flammable, high-energy fuel. Acetylene is so volatile that it becomes unstable. I mean, it can spontaneously decompose, just explode.
By itself.
By itself. At a pressure above just 15 pounds per square inch. 15 CI.
15. That's less pressure than in a car tire. How do you even store a gas like that?
That's the chemical magic, right? That's the dissolved part of its name. To keep it stable, they mix the gas with a solvent, usually acetone.
Acetone, like nail polish remover.
The very same. And that acetone is absorbed into this porous, sort of spongy filler material inside the cylinder.
So the acetone is like a chemical seatbelt for the gas.
A perfect analogy. It lets you store the gas safely at much, much higher pressures.
So the risk isn't just about pressure. It's completely tied to the state of that solvent inside the cylinder.
Absolutely. And you have other flammables on site, things like propane, and their risks are more straightforward ignition hazards. But the big overarching rule here is that the powerful oxidizer oxygen and these highly flammable fuels are chemically incompatible.
They are enemies.
Mortal enemies. And we can't forget the other risks either.
The physiological ones.
Right. In a closed space, any of these gases can just push out the breathable air and lead to asphyxiation. And of course, the trauma from an explosion or the severe burns from one of these accelerated fires.
So the key takeaway here is that you need to understand the specific chemistry. It's not just about being scared of a gas cylinder.
It's about awareness. That is the true foundation of prevention.
Okay, so we get the chemistry. But what happens when that silent accelerator, oxygen, meets the super unstable acetylene in storage.
Now we're moving from chemistry into the geometry of safety. And this is where the rules get incredibly specific.
This is where it gets really interesting.
It is, because storage is probably the single most critical preventative step. It's how you control those dangerous interactions before they can ever happen.
So what's rule number 1?
The upright mandate. It's non-negotiable. All cylinders, all the time, must be stored standing upright and secured with chains.
And this goes right back to what you said about acetylene. We know it's dissolved in acetone, so why is just tipping the cylinder over such a huge safety failure?
Because that upright position is what keeps the whole system in balance. It keeps that liquid acetone solvent where it belongs, soaked into that porous filler material.
Okay.
If you tip that cylinder on its side, the liquid acetone can actually separate, it can pool, or even escape the filler, leaving pockets of pure acetylene gas without its stabilizing solvent.
So you've just created a huge chemical instability.
Just by changing the angle.
That is an incredibly delicate system. You're literally holding its chemistry together with its physical orientation.
It really requires constant vigilance. And beyond that, the environmental rules are just as strict.
Like what?
Well, storage has to be in a well-ventilated, dry, and cool area. The manual is specific, below 52 degrees Celsius, or about 125 Fahrenheit.
So keep them out of the sun.
Absolutely. Away from direct sunlight, away from any heat sources, and away from corrosive stuff that could weaken the cylinder itself.
And, of course, they have to be secured.
Mandatory. Chained or strapped to a wall or a rack so they can't be knocked over. You also have to separate your fulls from your empties.
The empties are still a risk.
They still contain residual gas and pressure. And the valve protection caps, those big screw-on metal caps, they have to be on any time a cylinder isn't actively in use. They protect the weakest point.
All right, now for the big one. The rule everyone's heard of. Handling the enemies in storage. The segregation distance.
This is where we put that chemical incompatibility into practice. Oxygen, the oxidizer, has to be stored at least 6 to 20 feet away from any flammable gas.
6 to 20 feet. That's a pretty wide range.
Yeah.
On a crowded industrial site, 20 feet can feel like a mile. Why so much space?
The range really depends on the volume of gas being stored, the specific site layout, and making sure emergency responders can get access. It's an engineered buffer.
Is there a workaround if you just don't have the space?
There is. The manual provides a critical alternative. You can store them closer if, and only if, you separate them with a non-combustible wall.
Like a concrete barrier.
Exactly. It has to be at least 1.5 meters high, and it needs a fire rating of at least half an hour. That wall becomes the physical barrier that isolates the chemical conflict.
And the Rhino Project rules also worry about fire risks from the outside.
They do. No storing cylinders near combustibles like piles of wood, fuel cans, or even dry vegetation. They mandate locked outdoor storage sheds with a 3-meter clear space all the way around them.
So a grass fire can't reach the cylinders.
Precisely. And all of this has to be checked every single month. You check for damage, you do the soapy water test for leaks, and you check the expiry dates.
Okay, so the physics of acetylene demands we keep it upright, and that dictates how we store it.
And that same principle follows it right into handling and transportation.
Which brings us to the day-to-day stuff, the human element. If storage is tricky, moving these things feels even more fraught with risk.
It is, which is why the rules for handling are commandments, not suggestions. First, PPE.
Personal protective equipment.
It's non-negotiable. Safety glasses, gloves, steel-toed boots, and absolutely no loose clothing that could snag a valve or, worse, get contaminated with grease.
And how do you move them?
Only with a trolley or a cart designed for it. The manual explicitly forbids dragging or rolling them horizontally.
And there it is again. The ghost of the acetone problem.
It's the single most important rule to follow when they're in motion. Then you have transportation between work areas.
Right, on the project site itself.
The rules are just as strict. Cylinders have to be upright and secured, always in an open vehicle. Dissolved acetylene, because it's so volatile, should never be transported in an enclosed van or truck, period.
And you can't just throw them all in the back of a truck together.
No. Flammables and oxidizers, your oxygen and acetylene, cannot be transported together unless you have that same kind of stringent physical segregation between them.
And there are limits.
Strict limits. For small movements, like in a site Jeep, the max is 2 cylinders, and that vehicle must have a fire extinguisher on board ready to go.
Okay, so we get the cylinder to the work area safely. Now we have to actually use it. And there's a really smart, almost hidden safety feature here. The regulator fittings.
This is a deceptively simple and brilliant piece of engineering. The connections are made differently on purpose
Why?
to make it physically impossible to attach an oxygen regulator to an acetylene cylinder, or the other way around. Oxygen uses a right-hand thread, righty-tighty.
The settling.
It uses a left-hand thread. It tightens counterclockwise.
So even if you tried, you physically cannot cross-contaminate the systems. The threads won't match.
It's the ultimate mechanical failsafe.
That is brilliant.
It is. Then once you're connected, there are more safety steps. You have to purge the lines of any air before you light the torch, and the use of flashback arresters is mandatory.
And a flashback arrestor, for anyone who doesn't know, is what stops the flame from shooting backward up the hose and getting into the cylinder itself.
Which would be catastrophic,
Yeah.
an internal explosion. Proximity rules are also absolute. Work only in well-ventilated areas, and you need a 15-meter buffer zone around the work. No smoking, no sparks, no open flames within that radius.
And to recap the big nevers.
Never, ever use oil or grease on any fitting. And never, ever try to use a cylinder that you suspect is damaged.
So we've covered prevention from every angle, but things can still go wrong. We have to talk about what to do when an incident actually occurs.
Prepare for the worst. Response saves lives, but, as you'll see, specific, sometimes counterintuitive knowledge is what saves lives safely.
Okay.
For most leaks, the general procedure is what you'd expect. Evacuate the immediate area, increase ventilation, but there is a huge caveat for dissolved acetylene.
What's that?
If you have a leaking acetylene valve, you must never use a wet cloth on it.
Really?
Right.
That seems like a go-to first step for a small leak to try and slow it down. Why not here?
It's because of DI's chemistry. Acetylene can react with copper or brass, which are common in valve fittings, to form these incredibly sensitive explosive compounds. They're called acetylides.
And the water makes it worse.
Being wet or cooled rapidly can actually accelerate that dangerous reaction, making the valve itself highly unstable.
That is exactly the kind of critical detail that makes or breaks an emergency response. What about a fire? A cylinder is actually involved in a fire.
Use a CO2 or a dry chemical extinguisher. But the most important rule is cooling the cylinder. You have to spray it with water, but only from a safe distance.
Why from a distance?
Because that intense heat can compromise the cylinder structure, and you don't want to be anywhere near it if it ruptures. If the pressure relief device on the cylinder opens up and starts venting gas, don't try to stop it. Just keep cooling it from a distance and get everyone out of there.
And finally, there's accountability.
Right. This isn't a one-and-done training. Compliance demands annual site audits and refresher training every 6 months. It reinforces that this is an ongoing risk.
And reporting everything.
Everything. Any incident, no matter how small, gets reported to the site supervisor. If it's a major event, regulatory bodies like PISO have to be notified immediately. That reporting loop is how safety standards get better over time.
We have covered so much ground today. We've gone from the microscopic world of chemical reactions, oxygen accelerating, acetylene being unstable, all the way to the big spatial rules, like that 6 to 20-foot segregation.
And down to the tiny mechanical detail of a left-hand thread on a valve.
Exactly. These gases are absolutely essential for the kind of work they do at the Rhino Project, but you can see how they demand this extreme constant vigilance.
Absolutely. The sophistication of the rules just reflects the seriousness of the danger. I mean, think about that upright mandate for acetylene one more time.
Okay.
You're not just following some bureaucratic rule to stop a tank from falling over. You are actively preventing a fundamental chemical structure from breaking down inside that cylinder.
By keeping the acetone solvent in place.
The stability of the entire system hinges on that one simple action, keeping it upright. It elevates safety from just following a checklist to actually applying chemical physics in the field.
That really is the heart of this deep dive, isn't it? Understanding the why behind the rule.
It is. And it brings up a final thought for you, for anyone listening. We spent all this time talking about the absolute need to separate incompatible risks, oxygen from acetylene, with physical distance or a barrier.
Your enemies in storage.
Exactly. So how could you apply that concept of strict segregation to your own world? Think about the incompatible risks in your own work or life. Maybe it's incompatible software systems or opposing processes or even just conflicting personalities on a team. Identifying your own operational enemies in storage and then building the right kind of barrier or distance between them, that's the first step toward creating a truly stable, safe, and effective environment.